This episode is sponsored by Thimble and Brush Co. Thimble and Brush Co. makes one-of-a-kind, soft, comfortable, meticulously designed apparel and handmade decor so you and your home can look their best in unique style.
I am so excited to have them as a sponsor for this episode because I found this shop on Instagram and their stuff is so cute. They followed us. I went to check it out. I love the aesthetics. The shirts are so soft. If I could, I would buy absolutely everything in the shop. So go check it out. And if you do, we have a discount code.
Their shop is www.thimbleandbrushco.design. If you go check it out, and if you see something you like, no matter how many things it is, you can get a discount of 15% by using the discount code CHEM4LIFE. So that's CHEM, the number 4, LIFE at checkout. And now on to the show.
Hey, I'm Melissa.
And I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Jam, I'm so excited for today.
Why's that?
Well, you know why, because we have a very special guest today.
Yes, we do. And it's our first time ever having a guest, too, which is like double excitement.
Triple excitement because it's my sister.
Whoa.
I know,
Is
you're
that
so
allowed?
surprised. Well, she is a scientist.
Okay.
So I guess so. So we're going to go in a little bit different order today.
Okay.
I'm going to explain some chemistry stuff.
Okay.
If you're interested, I'm going to explain to you how thermometers work.
I'm very interested in that.
That's good. That's important to the premise of the show.
And you're talking like physical, like analog thermometers? Or
Thermometers with liquid in them.
okay, got it.
I don't know how digital thermometers work.
Yeah.
Computers, outside my realm. So I'm going to explain how thermometers work.
Okay.
And then I'm going to pass the baton along to Renee.
Okay.
She's going to explain some about her work and how that relates to the thermometer stuff. And then you'll be able to explain it all back to us. You'll be an expert on your own.
Whoa. Okay. I'm ready. So I still have to learn stuff. It's from two different people. But my job's the same. Okay.
Mm-hmm.
Got it.
And we'll talk more about her and all that she does when we get to that part. But she is coming to talk to us about essentially how thermometers are related to the sea.
Excellent. I'm
and
excited.
The oceans.
I'm excited for that and for the topic and for just having a guest in general would be awesome.
Me too. So let's get right in.
Okay.
Atoms and molecules. How thermometers work. You ready?
I'm ready.
Atoms and molecules are always in motion. I imagine them like little children, not during nap time.
Okay. So like any other time.
Any other time.
Uh-huh.
When they're not asleep, they're like bouncing around. They're moving. They're moving their arms and legs and they're moving around the house and they're doing all kinds of crazy stuff.
Yeah.
Especially think about like an 18-month-old.
Uh-huh.
That is a lot like how atoms and molecules work.
Okay.
Molecules have rotational motion. They're spinning. They have vibrational motion. They're vibrating.
Uh-huh.
They're stretching out and coming back together. They have all those different kinds of motion.
Okay.
And they're moving around in the air, moving back and forth around. So it's just like how a kid is wiggly and is running around.
Yes. They themselves are moving relative to themselves. And then also they are moving to the observer.
Exactly.
They're moving around, running around the couch, jumping on stuff.
Yes. To me, that is the perfect explanation of a molecule. And actually, there's a professor at the University of Miami in Ohio who makes her students imagine what it's like to be a molecule. Uh-huh. So they're like running around the classroom, flapping their arms, doing all kinds of crazy stuff. So I think that's fun.
That's so funny too, because it'd be natural for us if you asked like a 5-year-old to do it. And then you're asking these like college students to do it. And it's like, basically, you could think I'll be a molecule or I'll be a 5-year-old. It's like,
right.
It's like we need to go back to our roots and then we know what it's like to be a molecule.
And it really helps in getting the mental picture of what a molecule, the actual model of a molecule in your mind, if you have to put yourself in its shoes.
Yeah.
Sort of like how I want to shrink down and see how electrons work.
Yeah.
So the thing about that motion is if there's more energy put into the molecule, just like with a child, there's more motion.
Okay.
And if there's less energy put into it, there's less motion.
Okay.
that corresponds to heat and cool.
Heat, more energy, cool, less energy.
Yes.
Okay.
So if you're heating something up, those individual molecules are moving more.
Okay.
And because of that, they need and will create more space that they're moving around and filling up. Just like if a little kid is sick and tired, they're not taking up so much space. And if they're fully healthy and fully energetic, they basically take over the whole house. Yesterday, I was with my nephew who's maybe 18 months. And he really and truly was everywhere all the time. The kitchen, the living room, the bedrooms. Nothing was off limits unless the doors were physically closed. Just like molecules. And because of that, most substances, as they heat up, will expand.
Okay.
And most substances, as they cool, will contract.
Okay.
There are a few exceptions that have to do with the formations of solids and stuff, intermolecular forces. We don't have to get into those today. But that is a good general rule. So now, how do you think that relates to thermometers?
Okay. I'm not sure what is in thermometers. I think old ones had mercury. That's what I always heard.
Yeah.
Because they would be like, thermometer breaks or whatever.
Yeah, I broke a mercury thermometer on 2 occasions in the lab, and it was very stressful.
Yeah, that doesn't sound fun. So my guess would be that whatever is in the thermometer does that. It expands when it gets hot, condenses more when it's cold, but it'd have to be either like the perfect amount in there so that it'd do it corresponding to actual degrees, or I guess be the right kind of substance. I don't know.
Right.
How'd they do that?
You got it. So most thermometers that we use in the lab that have liquid, now they use alcohol, and they work by knowing roughly how much alcohol will expand for different temperatures. And so they build the little tube inside there and put the gradations on there corresponding to what the alcohol will move to when it heats or cools.
Interesting.
And that's it.
Alcohol. Not that I would know what other substance to use, but like, it's like all I've ever heard was mercury, and then the ones that look just like water, like that are
That's
red
the alcohol
or whatever.
ones, right?
Okay.
They just dye it.
Interesting.
Yeah.
Weird.
So that's it. That's how thermometers work. It's that simple.
That simple, but it probably took forever to figure out, or like at least a lot of smart people to get it to be right. Because like I could put some alcohol in a tube, and we'd have no idea what temperature it is still.
That's exactly right. Yeah, that's probably true.
I'd be like, yeah, it must be really full outside. Like it'd get really expanded and be like, wow, it's really full outside.
And there probably is some, if you heat a closed container, eventually it will explode. So there has to be some level of, there's a vacuum in there or whatever, so it can expand and contract without it exploding or whatever. But that's the basics. And that concept, we don't have a name for that really in chemistry. But when I hand it over to Renee, that concept is referred to as thermal expansion.
Okay.
When you're heating, things expand. We don't really use that term in chemistry. I'd never really heard it. We more just talk about kinetic energy and the motion of the molecules and heat and cool. And that's kind of it. But there is a name for that in her field, thermal expansion.
Okay.
So that's it. You know everything about thermometers.
Whoa.
You could make one yourself. Probably not.
Yeah, probably not. I don't know if my wife will let me handle any like dangerous chemicals like alcohol or anything. So,
okay, so that's it for me. That's it for my part today.
Okay,
you've learned all the chemistry you need to know.
That was kind of a nice like make me feel good. Like it wasn't crazy complicated. It didn't take you very long to explain to me.
Confidence builder.
Yeah. So hopefully now I have the confidence necessary to go into this other topic.
New situation.
Yeah.
So we're gonna have Renee. She is extension faculty at Mississippi State.
Okay.
I didn't know what extension meant, and for a long time I just joked that I have no idea what she does. But a good way to describe it is just she takes science that's already available and makes it to where people can make decisions with it. So that would be government, residents can make decisions with it that are informed by science.
Okay.
So sort of makes it usable for people.
Got it.
And she works in conjunction with Mississippi Alabama Sea Grant on this crazy thing that has a terrible name. It's awful. And she knows it's awful. Called Northern Gulf of Mexico Sentinel Site Cooperative.
Yikes.
So it's a mouthful. It's awful. Even the acronym is awful.
Are there any vowels in there? I was like trying to process it as you said it.
They do the O, I think, for Gulf of Mexico. It's like what is it? Ngom. It's terrible.
Yeah.
So I'll let you talk to her about that and ask her some questions.
Okay.
But that works in the same field of extension, specifically about sea level rise science into decision making on the Gulf of Mexico coast.
Okay.
So that's a little bit about what she does. And she does all that full time while working on her PhD.
Wow.
So she does
Yikes.
like twice the volume of work I do at least.
Yeah.
Even counting everything we do for the podcast.
Yeah.
And all my volunteer work. She's like amazing. So that's a little bit about her.
Awesome.
And now I'm going to pass the reins over to let her teach you about sea level rise.
Awesome. Hey, Renee, what's up?
Not a lot. I'm very, very excited to be here.
Yay.
Thanks for coming.
Yeah, thanks for having me.
So was that an accurate description? Did Melissa do a good job of explaining what you do?
It's pretty close. Yeah, I, like Melissa said, help make the science usable, but a lot of times it's actually physically being in the room and helping people use it.
Okay.
It's even if you make science really accessible and understandable, even when you hand it off to somebody, it's still intimidating. So a lot of times we're in the room helping them use it.
Got it. Taking data that's just data that maybe the person who has to make a decision about doesn't understand the data on its own.
Yeah. So like, for example, with sea level rise, there's a lot of maps like showing where water will go. And even though we have maps showing where the water will go, there's still a lot that people aren't sure about it.
Yeah.
And so being able to help answer questions and make them feel comfortable. So then when they make a decision 2 weeks later or a month later, they really get it. I didn't just hand them a map and walk away.
Got it. That sounds really helpful. I mean, especially because it would be very like a nightmare to think about people making decisions being handed just raw data and like that's it. Like that would make me not feel very confident in our current
Here's this
world.
map. Good luck.
Yeah. I think that's really cool. That makes a lot of sense.
Yeah, Extension has a long history of doing that. It started with helping farmers get access to agricultural science back in the 50s and 40s, I think maybe even earlier. And so there's institutions called land grant institutions, just like Sea Grant, and every state has land grant institutions. And so we've just continued that on from there on other topics besides agriculture.
Interesting. And extension too, it's not super intuitive to me, so it helps that you've explained that because like I think that's the phrase I might use would be like dumbing something down or like explaining or whatever it is to people who wouldn't understand it at the higher level. Basically what we do here for me. So
really the difference is Melissa does education. So there's like learning objectives. So people have knowledge. And then extension is about making decisions, whether it's on your farm or buying a house or building a city or something like that.
It's in motion. Something needs to happen. This information needs to be acted upon in some way or whatever.
Yep.
Got it.
But it is interesting. This is Melissa again, in case they can't tell. I'm worried. But it is interesting that we are in such similar fields just with different outcomes.
Yeah.
We do very similar work, but with different end goals.
Sweet. Okay, so that is what you do. And I'm guessing we're going to go beyond thermometers into something bigger, grander, scarier. I don't know. What are we going to talk about?
Maybe a little scarier than thermometers.
Yeah.
So
thermometers really scare me. So
that mercury, man.
Oh, yeah.
So like Melissa said, we really focus on sea level rise and its impact specifically, helping people make decisions around that. And so what I'm going to talk about today is how thermal expansion, how the molecules move and take up more space, has anything at all to do with that.
Okay.
And so to do that, we're going to take just a step back and look at the whole globe. And so we have our atmosphere, right? And the way the atmosphere works is sunlight can come in, but then some of it gets trapped here and helps make us warm because space is real, real cold. But when we use our cars and produce carbon emissions, whether that's CO2 is usually what we think about, it adds to the atmosphere. And so the atmosphere is kind of like a blanket. And as we have more and more carbon emissions, it makes that blanket thicker and thicker and thicker.
Got it. Okay.
And so it makes our planet warmer.
Yeah.
So if you think about your car, after it's been sitting outside in the sun and you get into it, it's much warmer than outside.
Oh, yeah. Yeah. I have like no tint on my windows at all. And even in the winter, if I've parked it conveniently in the sun, that happens to me, which is really nice. I mean, like not having tint is not great in other ways, but it's definitely nice whenever it's like cold outside, but still warm in my car.
How's that in the Texas summer for you?
That's horrible. Yeah. I just basically I get like cooked every time I get in. So there's already those gases in our atmosphere that help our planet be like bearably warm so that we can survive. But we are adding to that in the atmosphere. So we are kind of like basically making that effect stronger by what we do, the vehicles we use, the stuff we put in the air. Got it. Okay. So that was just already there, but the effect was already there, which was great, but we might be like making it too much there.
It's like adding an extra blanket in the winter.
Got it. Yep.
Yeah.
Or if you're in the summer and you put a blanket on and you're like, I don't really need one.
Yes, that's closer, actually.
Okay.
I don't really want this blanket anymore. Unfortunately, we can't just take the blanket off.
Okay.
It's going to take some work. But so because of that, because the world gets warmer, there are two things that affect sea level directly.
Okay.
And so before we can get into that, I just want to make sure we're all on the same page about what sea level even is.
Okay.
I think we've heard it referenced and how that works.
Yeah.
But essentially what happens is if you go down to, say, the beach and you're sitting there and you see waves, and then if you're there for like a whole day, you see that there's tides. People have heard of tides.
Right.
Water goes up and down. Like there's the Bay of Fundy, I think people have heard about, that has like an 18-foot tide or something crazy.
Wow. Gosh.
I might be too much.
I've never heard of that, but that is crazy.
Yeah, that is crazy.
In the Northern Gulf where I live, it's like 1.5 feet.
Okay.
That's a big tide for us.
Yeah.
So it's all different. So, but there's these perceptions of where sea level is that alter all the time. The ocean's always in motion.
Yeah.
But there's sort of like a starting point you can think about that those waves happen around, going up and down, and tides happen and go up and down. And if you think about events like hurricanes, which we've heard a lot about lately, then storm surge comes in. The starting point from which all those things happen,
Okay.
that itself is coming up.
Got it. Okay. So even though the ocean and the sea is always changing, it's obviously not like just perfectly still. There is a basic like number we've had to kind of keep in mind. It's like the
It's like
sea's
an average.
Yeah, it's like around here, and the around here is getting higher.
Yes.
Okay. Yikes.
So, for example, we know that high tide and low tide, right? We sort of know where high tide is. So the waves come up on top of high tide and are hitting at like a certain point.
Yeah.
And so the shoreline is ready for that. It's adapted to it. But with that starting point, with sea level going up, now the waves can hit higher. And so now storm surge can go even farther.
Yeah.
Things like that, right?
Right.
So there's two main causes that make the actual sea level, the starting point, go up.
Okay.
So one of them is that ice that's on land is melting.
Yes.
And so when it melts, it goes downhill into the oceans.
Okay.
So the actual amount of water in the oceans is increasing.
It's so crazy that we're talking about this now. I just, when we were in New Zealand a few weeks ago, just saw a glacier for the first time and saw all these points where they said like in, 1905 when they discovered it, it was here.
Yeah.
In 1960, it was here. And then they had a 10 years ago one. This was the Franz Josef Glacier in New Zealand. It was like in 2009, it was here. And we had to hike about 45, 50 minutes further past the 2009 point to get to where it is now. That's a 10-year difference. And so like I wouldn't have any real concrete like relatability to this, what you're talking about, other than just like I understand that things melt or whatever. But it's crazy to have seen that and then now be talking about this because like that must be a lot of ice that was just from that one glacier.
Can I ask a clarifying question?
Yeah.
Because I'm not an expert in this. Is there a difference between glaciers and icebergs and how they melt differently and what they do? Because I thought that glaciers were floating in the ocean until you just said you hiked.
Oh, yeah.
So there are some complicated things with ice sheets and what they're made of that I honestly don't understand all of it. But there is a big difference between glaciers and icebergs. So glaciers are not adding to the water
Okay.
when they're up and frozen because they're up and out of the way.
Yeah.
But an iceberg is floating in the water. So that's what we call sea ice.
Okay.
So if you think about an ice cube in your glass, when it melts, it doesn't overflow.
Right. It was already taking up space.
Right.
Okay.
So icebergs are floating about in the water. Glaciers and other types of land ice are on land. They're out of the way. They're not in the water, giving it more space. So when it melts, it comes down and then enters the water.
So icebergs are fine unless you're a Titanic.
Correct.
And then, but glaciers are a threat in terms of them. They have an effect.
Yes.
As they melt. Okay.
Yeah, they're like up solid on land.
Yeah.
And then when they melt, they come in. So glaciers are so big, like you said, because you hiked up them, they're massive, that they have their own gravitational pull. So it's this thing in science. I don't know if everyone knows this, but mass has gravitational pull.
Okay.
But usually it's something as big as a planet.
Right.
Or in this case, the glaciers themselves are so big that they sort of change the gravitational pull of the Earth, the where we're pulling at.
Oh my gosh. That's crazy.
And so part of that means they're pulling ocean water towards them.
Oh, interesting.
So when the glaciers melt, not only does their water enter the ocean, but it changes where the water in the oceans is hanging out at.
What?
And so when that glacier gets smaller and its gravitational pull gets less, then some of the water that's like piling up near the poles will end up other places like near the equator.
That's crazy. I can
or
like
in the Gulf of Mexico.
sort of barely get my head around that a little bit, but it's like not only is there water that melts from the glaciers having an effect on the sea, but also just they're changing mass.
Yes.
This is affecting the sea in a
Like
crazy
where
way.
it's distributed.
Yeah.
Yeah.
Oh my gosh.
So it's really cool and it's mind blowing, but it is pretty complicated. So don't worry about too much the process or get in too much depth, but it's so neat. I wanted to mention it.
Gosh, that is so cool and mind blowing and crazy. Thank you for sharing that. Especially, I think like I would be overwhelmed by that if I hadn't encountered a glacier recently. It would feel like, whoa. I'm learning what glaciers even are and that they have a way bigger effect than I ever thought. But that's awesome.
Yeah, it just goes to show how complicated all this science is. There's just so much cool stuff happening.
Yeah.
So that's one part of it, melting land ice. So just making the volume of water bigger.
Okay.
The other part of it is thermal expansion.
Okay.
So the actual molecules of water in the ocean that make it up experience those same forces from chemistry, just like Melissa talked about.
Okay.
And so as the oceans absorb all that extra heat that we're trapping in the globe, that means that the molecules get more excited. I anthropomorphize molecules. I make them sound like humans all the time.
Me too. I also do that, and some scientists get mad, but I think it's so useful.
Yeah.
It's so useful.
I think me and all the listeners are thankful that you guys are willing to do that.
Okay, good.
Great, good. Yeah.
So the molecules get more excited and they have more energy. And so then they're moving around more and more, which means they take up more space. And so if they're taking up more space, that sea level, that starting point goes up to reflect that extra movement.
Got it. The thermometer of the Earth.
Yes.
It's wow. Okay, so it also behaves just like a thermometer. It's going to get higher
Yeah. Higher.
with more heat.
Yeah.
Dang it. That's crazy.
Another way to think of it, rather than higher, is it has a larger volume.
Got it. So there's a space between, like, it's microscopic. It's tiny, tiny, tiny. But the space between all the water molecules, if it even just changed a little bit on all of them,
Right.
would be a big difference.
Because
Right.
there's so much ocean.
Got it.
And it's worth noting that the Earth itself on land, we haven't seen that much change with all this extra warmth we've generated because the oceans can absorb so much heat.
Got it.
So, and that's something we talked about in the specific heat episode, how water can take more heat than sand on land. So basically water's been looking out for us this whole time, right? It's been taking in this heat and we haven't experienced much change, but now it's almost getting to a point where it's taken in so much. It is being affected.
Yeah.
So I'm going to take a stab at the chemistry
Oh,
side.
nice. This is great.
This is, just to clarify, this is Renee, but I'm going to try.
Okay.
At the chemical level, you're adding more water molecules. That's the melting land ice.
Got it.
And you're causing thermal expansion. So they're getting more excited and moving around. So it's sort of twofold. There's more molecules and the molecules are more excited.
Got it.
Nice. Way to go. Chemist approved. The only change I would make is I would say at the molecular level.
Yeah.
But you're not a chemist, so it's fine. I'll let it slide.
So that's it. That's like why sea level itself rises.
Okay.
But it's important to keep in mind other things on land or other factors can influence what that looks like where you're at on a coast.
Okay.
So how we talked about waves and tides that change exactly how the water level is. There's other things that go into it. So
Okay.
all we talked about today was what makes the sea level, the starting point, itself go up.
Got it. Not like how coasts change or if things like weather over time or something like that, where that's obviously a factor, but it's not. We were talking about the ocean itself.
Yes.
Okay.
What's making the ocean itself change.
Okay.
So that's it. So now this is the part where you tell me.
Yes.
Okay, cool.
Okay.
I'm excited.
I think I've got it. I hope.
This is my test of my communication skills.
Nice.
So there's ice all over the world. We know that to be true, whether it's like on the top of a mountain or kind of in a valley like a glacier or whatever. And that ice is melting, whether it's like really fast, or like the glacier that I was at, or who knows how many glaciers there are. Some of them might be fine for a while, but that's all water that has not been in the ocean. It's been elsewhere, stored safely somewhere else. And over time, if all those, say there's like 100 glaciers, there's way more than that probably, but say there's 100, if all of them are trickling a little bit into the ocean, it's going to have an impact. So more water is being added to the ocean than there was before.
Yes. And there are people who are measuring all that all the time and
Got
getting
it.
better at how fast it's melting all the time.
Okay.
So yeah, perfect.
So there's more water, but at the same time, the thermometer of the earth, all the water, which there's plenty of, just like a thermometer, as it's getting warmer, is just taking up more space. The molecules are spreading out more a little bit. And even if water wasn't being added, if that was happening, the sea level could still just rise because the molecules are getting a little bit more spread out.
Perfect.
And that part is thermal expansion.
Yes.
Okay.
Good job.
So those are the two ways.
Yes.
Wow. Okay.
And the amount that each one contributes to sea level rise is changing. So remember how you're talking about here's after 50 years, here's after the past 10 years, and
Yeah.
how that was different spaces.
Yeah.
So in the past, it's been a lot of thermal expansion and not as much glacier melt.
Okay.
And I don't know the exact ratios, but now it's switching.
Oh, man, that's crazy. It's also just overwhelming to think about. Like, I have zero idea how much ice is out there that's melting. Like, the one glacier I experienced seemed like plenty to me, but there's probably so much more.
Yeah. And there, if we want to, we can link to it. There's a paper that came out recently that actually breaks down by some of the major ice sheets how much they're going to contribute. It was really neat.
So one question I still have, I guess, that I don't know if I understand yet is, but I kind of assume, is that it's bad for the sea to keep rising. Is that right?
Yes.
It doesn't sound like a good thing, but is that right? Is that right? That's what I think a lot of the general public, non-scientific people like me walking around that hear a little bit here and there just think like, that sounds like it's not good.
Yeah, no, it's not good. The coastal areas have a lot of people in them and a lot of really important infrastructure. And I think sometimes there's this idea like, oh, it's just rich people homes on beaches.
Right.
But actually, there's a lot of industry that is sort of foundational to, like in the United States, in our country, that happens in those spaces. So one thing is shipping and ports, and that industry makes up around a quarter or more of the national GDP in the United States.
Okay.
And all the infrastructure that lets that happen happens in the coast.
Right.
So as storm surge gets higher and goes farther inland and causes more damage with sea level rise, that'll be a problem. Even little things like, oh, salt water is getting in places it didn't used to, and we didn't build it to handle salt water,
Right.
will start wearing out. Or train tracks will start having water over them. Even little nuisance things like that will have a negative effect on our economy.
Right.
So that's sort of the macro level, what happens like for the whole country. But if you think about the individuals and the people and community and families that are there, their homes are at risk to more flooding when it hasn't ever flooded before. Their whole lives are going to be interrupted and impacted by this.
Right.
And sometimes we hear like, oh, well, people should just leave. But that's a really big and complicated problem and question. And there actually are some communities who have elected to try and leave because of sea level rise.
Got it.
And they are finding a lot of really practical and community challenges. First of all, money. Who's going to pay to move everybody?
Yeah.
But then on top of that, the economies, the cultural fabric of these places are important. And so how do you transfer a whole neighborhood and where do you put them? And so it's a really complicated topic. And you'd like to think, oh, that just impacts the people on the coast.
Yeah.
But it's going to impact our whole country as we try and deal with these challenges.
Oh my gosh, Renee, thank you so much for teaching us that and for being on the show in general. It's like, man, it's a fascinating topic and one I just knew nothing about at all. Thank you for taking the time to explain it at my level.
Yeah, thank you so much for coming and teaching me about this. I've learned in the past, but I would not have known anything about this if you weren't my sister. So I've learned a lot. And I think we get these big words that are so scary, like sea level rise and climate change and global warming or whatever.
Yeah.
And this made it not scary, very understandable. And, oh, okay, this all makes sense.
Yeah.
Thank you guys for having me. This has been awesome. On that same note of it not being scary, because I'm an extension, we like people to take this knowledge and then make themselves safer or prepared or ready for it. So I wanted to touch on a couple things that your listeners could do as individuals and then things they might be able to do in their communities.
Okay.
Because this happens at all scales.
Yeah.
So as individuals, one thing I don't think people think about is food waste. Because food waste contributes a lot of carbon into the atmosphere and then you don't even use the food, right? So be thinking about, is the ugly produce really, does it need to be thrown away or is it just a little ugly? Maybe I can eat it.
Yeah.
Or splitting meals at restaurants. And this is a little trick, but check your pantry and fridge before you go to the grocery store.
Right.
So little things like that. And we don't need people doing it perfectly, but we need a lot of people doing it imperfectly.
Got it.
So that's one. Another is thinking about ride sharing or minimizing the amount of time you're in the car, using public transit for people who have that option. Things like that. Every little bit, every time you drive one car instead of two, that helps.
Got it.
And so the third thing I just wanted to mention is thinking about how you heat and cool your home. So sort of two sides to this. You can make your house more efficient, which saves you money.
Yeah. Yeah.
Putting in insulation or new windows or things like that.
Yeah.
But from a really easy perspective, you can just change your thermostat when you walk out the door, right? So if you're going to be gone for 8 hours or more, it's better to turn your temperature up in the summer. So you're just not using your AC as much.
Got it.
And so that's less energy we're using. That's less carbon.
Okay.
So those are three ways an individual person can help reduce the fact that sea level rise will happen or as much.
Got it.
For people who live on the coast, you want to be thinking about it when you buy your house. You want to be thinking about flood insurance and making sure, even if it's not required, that you have it. Things like that. But that gets a little more complicated. You coastal people, give me a call. I'll help you out.
Okay, so that's the kind of stuff that if we had like maybe one person doing it wouldn't make a huge difference, which would be a bummer. But to think about it more like, okay, if I'm doing it and at least, some other amount of people are doing it, there's a collective effect of slowing potentially the rising of the sea by all of us ride sharing or all of us not buying too much food or wasting too much food or whatever. And that effect could just be cumulative if we all were trying to do our best.
Well, if you think about it, that's how we got here in the first place, is people individually generating a little bit more carbon than they would otherwise.
Got it.
So if we all generate a little bit less.
Yeah. We're in this together. It's a team effort.
Yep. So the number one thing that we can all do is to talk about this. The Yale Climate Center found that over 2/3 of Americans are concerned about climate change, but less than a third of them even talk about it.
Got it.
So at a community level, change won't happen if we don't all sort of agree it needs to happen. And so that's the biggest thing on our website. We have videos and like fact sheets on how to talk about it. But even if you just have a conversation and just make it more normal to talk about, that is one of the biggest things that we can all do.
Got it.
Nice.
Thank you so much for that. That's very helpful. It's like just hearing about something that I didn't know about before and not having any practical things that I can do would be scary. So thank you so much.
Yeah. Thanks for being willing to take action.
Well, thank you so much. This is so exciting. I'm so glad that we had you on, Renee.
Yeah.
Personally,
thank you.
it's fun for me to hang out with my sister, but also this stuff is so interesting and so important and so helpful. So
Yeah.
I'm really glad we had the opportunity to do that. Now I think we're just going to go ahead and wrap it up because we had Renee on, so it was a little different than normal. But I would like to give a shout out. It's so cool that Renee was here today because our parents, the day this episode comes out, it's their 38th wedding anniversary.
Nice.
Yay.
That's awesome.
Which is amazing that
Yeah.
they've had a relationship for that long. And so thank you guys for working hard on your marriage and giving us an example of that. And
for putting these two scientists out into the world.
yeah, for bringing us to life. So congratulations on 38 years, Mom and Dad. We love you so much.
Melissa and I have a lot of ideas for topics of chemistry and everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to the cost of making it, go to ko-fi.com/chem4yourlife and donate a cup of coffee.
This episode of Chemistry for Your Life was created by Melissa Collini, Renee Collini, and J.M. Robinson. References for this episode can be found in our show notes or on our website. J.M. Robinson is our producer, and we'd like to give a special thanks to A. Collini, who reviewed this episode.